Hello everyone, welcome back to my YouTube channel. I'm Basha studying at Shri Venkateshwara College of Engineering. Introduction to Register Allocation. Register allocation is a fundamental optimization technique used in compilers to efficiently manage the limited number of registers available on a computer's processor. It involves determining the best way to store and access variables in a program during execution. Talking about the importance of register allocation. It is important for efficient utilization of the hardware. That is, proper register allocation ensures that the CPU's registers are used completely and efficiently, maximizing the performance by reducing the need of expensive memory access. It is also important for code optimization. Efficient register allocation is crucial for compilers and interpreters to generate highly optimized code, leading to faster program execution. The third importance is memory saving. By minimizing the number of variables that need to be stored in memory, register allocation can significantly reduce memory usage and improve cache performance. And our next topic is register allocation strategies. The first strategy will be static allocation. It assigns register to variable at compile time based on the usage pattern. Simple but can lead to inefficient register utilization. And the second strategy is dynamic allocation. Assigns register to variable at runtime, allowing for more efficient utilization. Requires complex algorithms to determine optimal register assignments. And the third algorithm or third strategy is graph coloring. Represents variable liveness as an interference graph and uses graph coloring algorithm to assign registers. It minimizes the spills. And the fourth algorithm or strategy is priority based. Assigns register based on the priority of the variables, usually determined by the frequencies of use and lifetimes. Let's learn about the graph coloring approach. The graph coloring approach is a fundamental technique in register allocation. It models the program's variable as a vertices in a graph, where every edges represent interference between variables that cannot share the same register. The goal is to assign a color or a register to each vertex while minimizing the number of colors used, ensuring that the adjacent vertices have different color. Next topic on our list is interference graph construction. The first step is program analysis, where we analyze the program to identify the variables and their lifetimes. The next step is conflict detection, where we determine which variable interfere with each other. And the third step will be graph representation. Here we construct the interference graph based on variable conflicts. The first step in register allocation using the graph coloring approach is to construct the interference graph. This involves analyzing the program to identify the variables and their lifetimes, detecting which variables interfere with each other, and representing the conflicts in the form of an interference graph. The interference graph is crucial data structure that captures the relationships between the program's variable and will guide the subsequent register allocation process. Talking about register spilling and reloading. Register spilling is when number of live variables exceeds the available physical register. The compiler must have to spill some variables into the memory. This process of evicting variables from register is known as register spilling. Spill cost optimization is the compiler aims to minimize the cost of the spills by strategically selecting which variable to evict, considering factors like access frequency and register pressure. Reloading spilled values. When a spilled value is needed again, the compiler must reload it from memory back into the register. Efficient reloading strategies are crucial to minimize performance impact. Trade-offs in spilling. Register spilling involves a trade-off between register pressure and memory access. The compiler must find the optimal balance to generate efficient code. Now let's learn about register allocation algorithms. The first algorithm is optimal register allocation. Algorithms like kite bricks and iterated register coalescing aim to optimally assign variables to register, minimizing the need of memory access to and improving the program performance. The next algorithm is graph coloring approach. Register allocation can be formulated as graph coloring problem. where interference graph is colored using minimum number of colors or registers. The third algorithm is live range analysis. Algorithms analyze the liveness of variable to determine when they can share the same register, optimizing register use and reducing spilling the memory. Optimizing register allocation. Optimizing register allocation is crucial for improving the performance of computer program. By carefully managing the limited set of registers, compilers can reduce memory access and increase instruction level parallelism. Advanced techniques like graph coloring, filling, and reloading helps compiler find the more efficient register assignment. Integrating these algorithms with other optimization passes further boost code quality. Now let us understand the challenges in register allocation. The first challenge would be limited registers. Modern processors have a finite number of registers, often in the range of 16 to 32. This limited availability can make it challenging to efficiently allocate registers to all the program variables. The next challenge is spilling and reloading. When there are more variables than available registers, the compiler must decide which variables to keep in registers and which to spill to memory. Frequent spilling and reloading can significantly impact the performance. And the next challenge is irregular control flow. Conditional branches and loops can make it difficult to predict the lifetimes of variable, complicating the register allocation process and potentially leading to the suboptimal decisions. And the next challenge is architectural constraints. Different processor architectures may have unique register, file structures, calling conventions, or other constraints that must be taken into account during the allocation of the register. Conclusion and future directions. In this presentation, we have explored the critical role of register allocation in optimizing compiler performance. As we conclude, it's important to consider the future directions and ongoing challenges in this field. Thanks for watching. See you in the next video.